In this video, we'll talk about power functions and polynomial functions. Let's start with power functions, and let's start with the definition. A power function is any function that can be written in the form that you see here. F at x equals k times x to the p. K is a constant. We call k the coefficient. X is a variable, and p is another constant. P is called the power. K and p can be any real numbers. As an example, let's talk about the area of a circle. The area of a circle having radius r is given by the formula pi r squared. We can define a function using this formula. A evaluated at r is equal to pi r squared. This gives us the area of any circle having radius r. This is an example of a power function. Now let's see if we understand the definition by looking at some examples. Are the following functions power functions? Yes or no? Let's start with a. The function a at x equals 4 times x to the 25. This is a power function, so yes, power function. This one has k equal to 4 and p equals 25. What about b? b equals 2 divided by x squared. We can rewrite this one so that it is in the form of a power function, 2 times x to the negative 2. So yes, this is a power function. This is a power function where k is equal to 2 and p is equal to negative 2. p is allowed to be equal to a negative number. What about c? c at x equals 3. This one's also a power function. This is 3 times x to the 0, so this is indeed a power function. It's also a constant function. This one has k equals 3 and p is equal to 0, but that's okay that p is equal to 0. What about d? d at x equals the square root of the quantity 7x. So once again we rewrite it. This is the square root of 7 times the square root of x, but we can write that as x to the 1/2. The square root of x is x to the 1/2, so that's x to a power. So this is indeed a power function. In this case, k is equal to the square root of 7 and p is equal to 1/2. So it's okay if p is not an integer. P can be equal to 1/2. What about e? e to the x equals 3 to the x. This one is not a power function. Not a power function. In this case, we have a function which is called an exponential function. The next function, f at x, is equal to 2x squared plus 5x cubed. This is also not a power function. Not a power function. On the other hand, it's the sum of two power functions. 2x squared, that's a power function. 5x cubed, that's also a power function. But if you add them together, that's not a power function anymore. That's what we call a polynomial function, but it's not a power function. What about g? g at x equals 2x squared times 5x cubed. Notice that these are the same two power functions. In f, we added them together, and that was not a power function. In g, we're multiplying them together. Now that is, in this case, this is a power function, because if you multiply these together, 2 times 5 is 10, then x squared times x cubed is x to the 5th. And this is a power function. In this case, we have k is equal to 10 and p is equal to 5. A power function doesn't always look like a power function, but if you simplify it, it has to have this form, k times x to the p. Our last example is h at x equals 2x squared divided by 5x cubed. So these are again the same two functions. First we added them, then we multiplied them, and now we're looking at their ratio. We're dividing one into the other. This is also a power function. if we rewrite this, well, there's not much you can do with the 2 over 5, but x squared divided by x cubed is 1 over x. But that is the same as 2 over 5 times x to the negative 1. This is a constant times x to a power, so this is a power function. In this case, k is equal to 2 over 5, and p is equal to negative 1. So it is a power function. Let's talk a little bit about what we call the end behavior of a power function. The end behavior is what's happening with the graph of the function as x goes towards infinity or negative infinity. If f at x is equal to kx times p, like you see here, and let's assume that k is positive, and let's assume that p is an even positive integer. In that case, the graph will resemble a parabola, opening upward. The fact that k is positive, that's what makes it open upward. Since p is an even positive integer, that means x to the p is x raised to an even number. And if you take any number and raise it to an even number, you're going to get something positive. So because of that, since k is also positive, that means that your graph is going to open upwards. So it resembles a parabola opening upward. It's not actually a parabola unless p is equal to 2, but they have the same basic shape. The main difference is that the larger the power is, the flatter the curve gets at 0, at the origin of the xy plane, around this point with coordinates 0, 0. As you can see, the larger the power gets, the flatter the curve gets, but also the narrower it gets. You can see y equals x to the 8. This one is the most narrow. That's because when the power is bigger, your function is going to give you output values that are growing very quickly, faster than the other ones. So x to the 8 grows faster than x to the 4, which grows faster than x to the 2. So that means it's getting bigger faster. So that means the graph appears narrower. But x to an even power always has sort of the same shape. It looks vaguely like a parabola, but it's only a parabola if p is equal to 2. The end behavior is what's happening to the graph as x goes to infinity or negative infinity. In this case, as x goes to infinity or x goes to negative infinity, your output values are growing without bound. As you can see in the graph, they're growing without bound in either direction. They're getting larger and larger and larger. So as x moves to the right, the graph moves up. As x moves to the left, the graph moves up. So you can see that f is growing without bound, or in other words, f at x is going to infinity. Well, that's what we call the end behavior. If k is negative, then everything is reflected through the x-axis. These are the same graphs that you see, except now there's a minus sign in front. So this graph here is y equals minus x squared. If we scroll backwards, you can see this graph is y equals positive x squared. And here it's minus x squared. And all of these other graphs are minus x to the even power. And now you can see that they're parabolas that are opening downwards. X squared is always positive, so if you put a negative number in front of it, then that means the result is always going to be negative. That's why it's opening downward like this. In this case, when k is negative and p is an even integer, you can see that f at x is going to negative infinity as x either moves to the right or to the left. As you move to the right, it decreases, but also as you move to the left, you can see that the values, as x moves to the left, the values of y get smaller and smaller, decreasing without bound. So that's what we mean when we say that f at x is approaching negative infinity. It's decreasing without bound. These graphs represent the case where k is positive and p is an odd positive integer. In this case, as x moves to the right, your values for f, your output values, will increase. And you can see that in the graphs here. As x moves to the right, your output values are getting larger. On the other hand, as x moves to the left, x goes to negative infinity, x moves to the left, you can see that the values of f are getting smaller. So as x moves to the left, you're decreasing without bound. So what that means is that as x goes to positive infinity, f at x goes to positive infinity. But as x goes to negative infinity, f at x goes to negative infinity. That's why you have this distinctive shape. Again, all of these look roughly like y equals x cubed. Well, when you have y equals x to the 1, that's a straight line. But after that, they all look roughly like y equals x cubed, but they just get flatter and flatter at the origin the larger your exponent becomes, the larger your power. And again, it becomes narrower because the values are increasing in magnitude or in size faster the larger the power is. In these graphs, you have the same graphs, but we've just reflected them through the x-axis. So here we're looking at f of x equals k times x to the p, where p is an odd positive integer, but now k is negative. So everything is just reflected through the x-axis. Now as x moves to the right, f of x goes to negative infinity, which you can see here, and as x goes to the left, f of x goes to positive infinity, as you can see here. Here we have power functions where you're looking at x to a negative number. F of x equals k times x to the negative p. Now p is an even positive integer. P is positive. P is a positive integer, so that means x is raised to a negative number. P is positive, so this is the opposite of p. So negative p is a negative number, x to the negative p. Another way of writing this is k over x to the p. So in this graph, we're letting p be even, and k is a positive number. So if p is even, then x to the p is always going to be positive, and k is positive. That's why everything is above the x-axis. Everything is non-negative here. In this case, as f at x goes, or rather, what I mean to say, as x goes to negative infinity or positive infinity, so if you're looking at the end behavior, as x goes to infinity or as x goes to negative infinity, you can see that the output values are going to 0. That's because you have the x to the p in the denominator. As x gets larger, x to the p is a larger and larger number, but it's in the denominator. So you're dividing by a very large number, and that's why you end up very close to the x-axis, because y is very small. It's the same if you let x go to negative infinity, because even though x is negative, x to the even number is positive, and you're dividing by that positive number. So you're going to get something which is getting closer and closer to 0. X to the p is getting larger and larger and larger, so you're dividing by something which is larger and larger and larger, so your result is going to be something that gets smaller and smaller and smaller. So as x goes to infinity or x goes to negative infinity, f at x goes to 0. And that's what you see here. Now notice that there's some very strange behavior as x gets close to 0. As x gets close to 0, and this is not end behavior, this is what we call local behavior. As x gets close to 0, the values of f at x increase without bound. As x gets close to 0, you're dividing by a smaller and smaller number. And so your result is going to be larger and larger and larger. So imagine that you're dividing by some number which is really close to 0. You can imagine trying to plug in 0.1, and then 0.01, and then 0.001, 0.00001. The smaller the number that you put in for x, the larger the output will be. And that's why you see that you have this gap in the middle, because 1 over x to the p is getting very large as x gets close to 0. X equals 0 is not in the domain of any of these functions because we're not allowed to have 0 in the denominator. And that's why you get this behavior where as x gets closer to 0, f at x gets closer and closer to infinity. It's increasing without bound. Here we're looking at f of x equals k to the x minus p. This is the same function, where p is now an odd positive integer. K is a positive number, and p is an odd positive integer. So now we get two different behaviors depending on whether or not x is positive or negative. If x is positive, when you raise it to an odd number, you get a positive number. However, if x is negative and you raise it to an odd integer, you're going to get a negative output. And that's why when x is negative, these curves are all underneath the x-axis. So it's positive when x is to the right of the y-axis, but it's negative when x is to the left of the y-axis. Otherwise, you have the same sort of behavior. The end behavior is certainly the same. As x moves further to the right, or as x moves further to the left, the y values are getting closer to 0. And for the same reason, as x moves to the right, you're getting a larger and larger number in the denominator. And so when you divide by a large number, you get a small number. On the left side, you're dividing by a large negative number. And so you're going to get a very small negative number, small in the sense of its size. So it's close to 0. On the other hand, as x moves close to 0, you're dividing by something very small, so your result is going to be a large number. As x gets close to 0 from the right, which we use this notation, this means that x is approaching 0, and when you have this little plus symbol, that means x is 0 plus something. 0 plus something is slightly larger than 0, so that means you're over here. So as x gets closer to 0 from the right, the values of f at x become increasingly large. On the other hand, as x gets close to 0 from the left, so x approaches 0. So when you have this little minus sign here, 0 to the minus, that's 0 minus something. So x is 0 minus something. It's slightly smaller than 0. So that means it's to the left. In this case, you're dividing by something really close to 0, so your result is going to be a huge number, but it's going to be a huge negative number. It's a huge negative number. So as x approaches 0 from the negative side, from the left, the values of f at x are approaching negative infinity. They're decreasing without bound. If k is negative, then the graphs are just reflected through the x-axis. So when p is even, you have graphs that look like this, and when p is odd, you have graphs that look like this. Everything's just reflected through the x-axis. So far we've been looking at power functions where the exponent is an integer, but it doesn't have to be an integer. Here you see functions that look like f at x equals k times x to the 1 over p. That is, it's the pth root. X to the 1 over p is the pth root. So here we're allowing k to be positive and p to be even. Now in this case, the graphs all look sort of like the square root. Again, they're a little bit flatter as you move towards the origin. You can see that they're flatter over here as p gets larger. The larger p is, the flatter they become. But notice it's vertical this time. It's a vertical flat instead of a horizontal. And the larger that p is, p equals 4, p equals 6, you can see that the outputs are smaller. Now, in all of these cases, f at x is going to infinity as x goes to infinity. So as you move further to the right, all of these are increasing without bound. They're all eventually going to infinity. However, the sixth root of x, it's quite flat. That means that it's growing and it's going to infinity, but it's doing it slowly compared to the other curves here. So this one will eventually become arbitrarily large. It grows and grows off to infinity, but just not as fast as the square root of x. That's because the sixth root of x is much, much smaller than the square root of x, and that's why you see that in this graph. Now, you notice that they all intersect here. This is actually at the point 1, 1. They all intersect at the point 1, 1. So this is 1 right here. So you'll notice that everything swaps at the point 1, 1. That's because when you take the square root of a number which is less than 1, you actually get something smaller than the sixth root. That's because these are all fractions over here. These are all 1 over something, like 1/2, 1/8, 1/10, that kind of thing. So these are really small. So when you compute the sixth root of something over here, you actually get something bigger than the square root. But once you're bigger than 1, all of that changes. So as x moves further to the right, everything grows without bound. It's just some of it might be growing slowly. Now notice the domain here is the set from 0 to infinity. That's because x to the p is always non-negative if p is even. So x to the p is the inverse of the pth root. So that means since this range is always non-negative, the inverse, which is the pth root, will have domain non-negative numbers. In other words, you can't take the square root of a negative number. You can't take the fourth root of a negative number or the sixth root of a negative number. And if you do, you get something which is not real. You get complex numbers, but we're just talking about real numbers. So that's why the negative x values are not in the domain of these functions. Now, on the other hand, if p is an odd positive integer, it's perfectly fine to have an odd root which is negative. You can take an odd root of a negative number and get a negative number. So the domain for these power functions, f at x equals k times x to the 1 over p, the domain is all real numbers if p is odd. Now in this case, as x moves to the right, you get the same sort of behavior as x to the p when p is even. So you'll notice that here you get shapes that look like the square root. And the same is true here for the odd roots. The shapes are basically the same. And they're all increasing to infinity. But again, the larger the root, the slower it increases to infinity. But these shapes are all basically the same as the even roots. The only difference is now you are allowed to use negative numbers in the domain of your function. And now you can see as x moves to the left, these functions decrease without bound. So as x moves to the right, you increase without bound, going to infinity, and as x moves to the left, they decrease without bound, going to negative infinity. Once again, if k is negative, then the graphs are reflected through the x-axis. So then you have this sort of thing. So you'll notice that if in these graphs you're looking at y equals the opposite of the pth root. So the pth root of x is going to be a positive number. So if you put a negative in front, you just end up with something negative. And you get the same thing here where you're reflecting through the x-axis. These are the same graphs, just reflected through the x-axis, because we put a negative sign in front. This leads us to what we call polynomial functions. A polynomial function is any function that can be written in this form. It's the sum of power functions. So this is supposed to be a power function, so that should be an n right there. F at x is equal to a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so on and so forth until we get to a sub 2 times x squared plus a sub 1 times x to the 1 plus a sub 0 times x to the 0, if you want to think of it that way. So a polynomial function is the sum of power functions. The subscripts on these a terms, a sub n minus 1, a sub 2, a sub 1, and so on, these are all supposed to identify the term as the coefficient of a power function where the power is n, or n minus 1, or 2, or 1, or so on. So a sub n is the coefficient of x to the n, a sub n minus 1 is the coefficient of x to the n minus 1, a sub 2 is the coefficient of x to the 2 power, and so on and so forth. N is a non-negative integer, but it can be 0, which is the case here. A sub 0 times x to the 0. This is an nth degree polynomial, so what that means is that a sub n is not 0. If a sub n was 0, then we would just get rid of this term, and then we would call it an n minus 1 degree polynomial. So you don't put in the leading term if it's 0. So I've just given away what that's called. That's called the leading term. So as I mentioned, these numbers a sub 0 up to a sub n, these are the coefficients. N is the degree of the polynomial. A sub n is the leading coefficient, and a sub n x to the n is the leading term. The leading term determines most of the end behavior of a polynomial, and we'll talk about that. If n equals 2, then the polynomial function is a quadratic function. So if n is equal to 2, then you just have these terms right here, and that's a quadratic function. If n is equal to 1, then you just have these two terms, and then you have a linear function. If n is equal to 0, then you have only this term, and that's a constant function. In this example, we're given several functions, and we're asked if they're polynomial functions or not. And if they are polynomial functions, we're asked to identify the degree and the leading term. So let's take a look. So a at x is equal to 2x to the 4 plus 3x to the 5 minus 21. This is the sum of power functions. So yes, this is a polynomial function. The degree is n equals, well, it's not, you might think it's 4 because that one's first, but it's actually 5. The degree of the polynomial is the largest degree of the largest power, I should say, of the power functions. It's just not written in the right form. Well, when I say the right form, I mean the general form. When a polynomial function is written in this way, with all of the exponents written in decreasing order of size, that's called general form. In this example, it's not written in the general form. The general form would be a at x equals 3x to the 5 plus 2x to the 4 minus 21. This is the same polynomial. It's the same function. I've just written it in a slightly different way. I've just reordered the terms. So the degree here is 5, and the leading term is 3x to the 5. So this is the leading term. What about b? b at x is 7x squared plus 2x minus 1 plus 3 over x. This is not a polynomial function. This is not a polynomial function because of this term right here. 3 over x equals 3 times x to the negative 1. This is a power function, but all of your powers have to be positive. If we go back to the definition, a polynomial function is any function that can be written in this form, where n is a non-negative integer. All of these exponents are non-negative integers. This is x to the 1, and this is x to the 0, but you can't have a negative integer. Here we have a negative integer, so b is not a polynomial. Because we have an exponent which is negative. What about c at x? c at x equals 3x. This is indeed a polynomial. It's a polynomial. The degree is equal to 1, because this is 3x to the 1. And the leading term, well, there's only one term here, so the leading term is 3x. So the leading term equals 3x. d at x equals 4. This is also a polynomial. This is 4 times x to the 0. So this is a polynomial. It's also a constant function. It's a polynomial. The degree in this case is 0. And the leading term, well, again, there's only one term. Leading term is 4. What about e at x? This might not look like a polynomial function, but it is. It's just not written in the general form. if we distribute that negative x squared, this is minus 7x squared plus 3x cubed. Well, I guess normally to write it in general form, we want the largest exponent first. 3x cubed minus 7x squared. So this is a polynomial. In this case, the degree is 3, and the leading term is 3x cubed. So this is the leading term. And the degree is 3. Okay, what about f? F at x is 3x cubed times 2x to the 4. Well, we can simplify this. 3 times 2 is 6, times x to the 3 plus 4 is 7. This is a polynomial. It's a power function where the exponent is a positive integer. So this is a polynomial. The degree is 7. And again, there's only one term, so the leading term is the only term that's there, which is 6x to the 7. What about g? G at x equals 2 times x to the 3 halves plus 3 times x to the 1 half plus 5. This is the sum of power functions, but the exponents are not integers. They're not positive integers, they're not even integers. In order to be a polynomial function, the powers have to be positive integers, or at least non-negative, because you can have constant terms. These are not integers, so this is not a polynomial. This one is not a polynomial. The end behavior of a polynomial function is determined by the leading term. Again, by end behavior, we mean what's happening with the graph as x moves further to the right or further to the left. The first graph that you see here is a degree 4 polynomial function. So the leading term is 3x to the 4th. This is a positive constant times x to a positive even number. So that means it, roughly speaking, resembles a parabola opening upwards. Now, certainly this doesn't look like a parabola because you've got this little bump in the middle, but we're talking about end behavior. The end behavior is determined by the leading term. The leading term is 3x to the 4. So that means it's above the x-axis, so it's going off to infinity, as you can see here. On either side, it's going off to infinity. It's opening upwards. As x goes to the right, y is increasing to infinity, and as x goes to the left, y is increasing to infinity, just like it is for 3x to the 4. Now, our second example, g at x, the leading term, this is a degree 3 polynomial, and the leading term is minus x cubed. Minus x cubed. Now, this does not look like minus x cubed exactly, because it's decreasing, then increasing, and then decreasing again. But notice that the end behavior is the same as minus x to the 3. In particular, there's a negative sign in front. So that means as x goes to infinity, as x moves to the right, the y values are going to negative infinity. And as x goes to the left, the y values are increasing. Here we have our function h. This is a degree 5 polynomial. So our leading term is 1/2 x to the 5th. And you can see as x moves further to the right, you're increasing. And as x moves further to the left, the y values are decreasing. In this case, our k, our constant, is 1/2, which is positive. So x to the 5th is positive as x moves to the right. So that's why it's increasing without bound. And as x moves to the left, x to the 5 is negative. So that's why it's decreasing without bound. Our next example is degree 8 polynomial. But notice that the leading term has a minus sign in front of it. Minus 4 times x to the 8. So that gives us this open down shape. The fact that there's a minus in front of the leading term, or the leading term has a negative 4 as a coefficient. So since it's negative, that means it's opening down. So as x moves to the right, or as x moves to the left, the y values are decreasing. Now the local behavior of polynomial functions is what we have in the middle. So if we're looking at what's going on in the middle of these graphs, that's what we call the local behavior. So the local behavior of a graph is what happens in the middle. So there are three things to look for: the y-intercept, where x is equal to 0, the x-intercepts, where y is equal to 0, and what we call the turning points, where it changes from increasing to decreasing or from decreasing to increasing. Now notice I say the y-intercept because there's only one of those. And I say the x-intercepts because there can be plural, there can be many. There might be none, but there can be many. Let's look at an example. The function graphed below is the fourth degree polynomial function f at x equals 1/3 x to the fourth minus x cubed minus 13 over 3 x squared plus 9x plus 12. This is a degree 4 polynomial. That's the leading term. So you'll notice, for example, that since k is positive, it's 1/3 is positive, as x goes to the right, you're increasing without bound, and as x goes to the left, you're increasing without bound. This graph has one y-intercept, which is right here. So that's the y-intercept. And it also has 4 x-intercepts. There's 1, 2, 3, 4. So x-intercepts. So there are 4 of them. It also has 3 turning points. Let me just change the color here. So there's a turning point right there, there's a turning point right there, and there's a turning point right there. So there are 3 turning points. The turning points are where it changes from decreasing to increasing or increasing to decreasing. So our first turning point is where it changes from decreasing to increasing. So that gives us a little valley. This turning point in the middle is where it's increasing and then decreasing. So that gives us a little hill. Then we're decreasing but change to increasing. That gives us a little valley. So these little valleys give us what we call local minimums or local minima. And these peaks or these little hills give us local maxima. So whenever you change from decreasing to increasing and get a valley, or from increasing to decreasing and get a peak or a hill, these are what we call turning points. Notice that all polynomial functions have one y-intercept. That's because if you have a polynomial function, the domain is the set of all real numbers. So that means you can plug in x equals 0, and that will give you the y-intercept when x is equal to 0. But there can only be one y-intercept, because if there was a second y-intercept, then it would not pass the vertical line test, rather. If there was another y-intercept, it would not pass the vertical line test and wouldn't be a function. So that means all polynomial functions have one and only one y-intercept. The x-intercepts occur where y is equal to 0. So the polynomial from the previous example can be factored to more easily identify the x-intercepts, and I've done that here. Now this isn't necessarily an easy thing to factor, but you can factor it. And then it looks like 1/3 times x minus 4 times x minus 3 times x plus 1 times x plus 3. This is equal to 0, so if we set this equal to 0, that will happen precisely when one of these factors is equal to 0. So either x is equal to 4, or x is equal to 3, or x is equal to -1, or x equals -3. So these are the x-intercepts right here: 4, 3, -1, and -3. And if you look back at the graph, you can see that. So there's an x-intercept at 4, 3, -1, and -3. Here's a theorem. A polynomial of degree n will have at most n x-intercepts and at most n-1 turning points. So let's look at an example. So these are the same functions that we looked at before, and this example will continue down here. These are the same functions we looked at before. So identify the degree n of each polynomial. We already mentioned that, but then we want to count the number of x-intercepts and the number of turning points. So let's do that. So for a, our degree n is 4. So n is equal to 4. What about the number of x-intercepts? The x-intercepts are where it intersects the x-axis. The x-intercepts are where it intercepts the x-axis, and you can see it never does. This graph is entirely above the x-axis, so it never intersects. So that means there are 0 x-intercepts. So there's 0. What about turning points? There can be at most n-1 turning points. And we have a turning point right here, and right here. So there are 3 turning points. N is equal to 4, and we have n-1 turning points. Okay, well, what about example B? This is a degree 3 polynomial, so n is equal to 3. And the x-intercepts, how many of those are there? Well, there's 1, 2, 3. If the polynomial function is degree 3, you can have at most 3 x-intercepts, because a polynomial of degree n will have at most n x-intercepts, and n-1 turning points. What about turning points here? There's 1 and 2, so this has 2 turning points. So turning points are 2. There's 1 right there, and 1 right there. So let's do this for the other 2 examples that we looked at before. So for C, this is a degree 5 polynomial, so n is equal to 5. And what about the x-intercepts? There's 1, 2, 3. You won't always have the same number of x-intercepts as you do degree. So the theorem says that a degree n polynomial will have, well, let's just scroll up and look at it. A polynomial of degree n will have at most n x-intercepts and at most n-1 turning points. That means you might have fewer than n x-intercepts. And in this case, we have 3 x-intercepts, which is fewer than n equals 5, which is the degree. What about the turning points? Well, there's 1 there and 1 there. So there are 2 turning points. So turning points, 2. What about our last example? So this is degree 8. So n is equal to 8. What about the intercepts? Well, there are only 2. And what about the turning points? Well, there's 1 right there, and there's another one right there. So there are 2 of those as well. You can see it's increasing, and then actually it's still increasing. So in fact, there's only 1, because it's still increasing right there. It doesn't change from increasing to decreasing. It almost looks like it's about to, but it doesn't. So in fact, I made a slight mistake there. There's only 1 turning point. There's only 1 turning point, and it's right there. So if you have a degree n polynomial function, you'll have at most n x-intercepts and at most n-1 turning points. But you can see you can have far fewer than that. This is a degree 8 polynomial function, but I only have 2 x-intercepts and only 1 turning point. So in this example, we're asked to determine the intercepts. So here, notice our dependent variable is t. Let's say our independent, so that's our independent variable rather. Our independent variable is t, so let's say our dependent variable is y. So let's say that this is y equals f at t, because we want to know what the y-intercept is as well. So the y-intercept, that's when t is equal to 0. So f at 0 is equal to 1/4 times, and now you just plug in t equals 0. So it's going to be 2 times negative 3 times 4 times negative 1. Negative 1. So this 4 will cancel with that 4. This minus sign times that minus sign will give you something positive. So you have 2 times 3 times 1 is 6. So the y-intercept has x-coordinate 0 or rather t-coordinate 0 and y-coordinate 6. But now we want to find the t-intercepts. So they're t-intercepts because our variable is t here. The t-intercepts occur precisely when y is equal to 0. So y is equal to 0 when one of these factors is 0. So in order to determine the t-intercepts, we just need to figure out what t's make this equal to 0. So we have t equals negative 2 for this one. For this one, we're going to have t equals 3. For this one, you just solve that, you set that equal to 0. 3t plus 4 equals 0, and then solve for t. So that means t is equal to subtract the 4, and then divide by the 3. And finally, we have this term right here, and that's equal to 0 precisely when t is equal to 1/2. So these are the t-coordinates of our t-intercepts. T equals minus 2, t equals 3, t equals negative 4/3, and t equals 1/2. So if you want to write them as points, that's going to be minus 2 comma 0, 3 comma 0, then we're going to have minus 4/3 comma 0, and finally 1/2 comma 0. So we have 4 of these. All right. Well, here we have another function. This is a function of s. So our independent variable is s, and our dependent variable, we can just call that y again. So y is equal to g evaluated at s. So first we'll find the y-intercept, and that's again where s is equal to 0. So g at 0 is 0 to the 4th minus 5 times 0 cubed plus 6 times 0 squared, which is 0. So the y-intercept is 0 comma 0. What about the s-intercepts? Well, we need this to be equal to 0. So this one isn't factored for us, but we can factor it. So s to the 4th minus 5s cubed plus 6s squared equals 0. Notice that they all have s's in them, so we can actually factor out an s squared. And that's going to give us an s squared minus 5s plus 6 equals 0. And we can also factor this term. So s squared times, so it's going to be s times s gives me the x squared, then it's going to be minus 3 minus 2. So then we have minus 3 times minus 2 gives me positive 6. Minus 3s minus 2s gives me a minus 5s. And this is equal to 0. So the s coordinates of our s-intercepts are s equals 0, s equals 3, and s equals 2. Now I seem to be running out of space here, so we'll just leave it like that and move on to our next example. So for this example, we're given a graph, well, we're given two graphs, and we're asked to determine if it is possible that it is a graph of a polynomial function. If it could be a polynomial function, what is the smallest possible degree? Okay, well, let's look at A. This could be a polynomial function. It looks kind of like a cubic, maybe not exactly, but this one could be a polynomial function of degree 3. It has to be at least 3 because we have a turning point there and a turning point there. So there are 2 turning points, so the degree has to be at least 1 higher. What about B? Well, this one could also be a polynomial. Could be a polynomial. It has three intercepts. So that means that the degree has to be at least 3. But let's also look at the turning points here. So if we look at the turning points, there's one there, one there, one there, and one there. There are 4 turning points, so that means the degree has to be at least 5. Could be a polynomial of degree greater than or equal to 5. But it certainly has to be odd. It has to be an odd polynomial, an odd degree for this polynomial. What about these two? Neither of these can be polynomials because they don't have the right kind of behavior. For example, if we look at the first one here, this one has a vertical asymptote somewhere. In particular, the domain is not minus infinity to infinity. In order to be a polynomial, the domain must be all real numbers, or the set of all real numbers. So this is not a polynomial function. What about this one? This one doesn't have the right end behavior. The first one here, C, this one didn't have the right local behavior. This one doesn't have the right end behavior because a polynomial has to go to either infinity or minus infinity as x moves to the right or to the left. So this one is also not a polynomial. So, because it has the incorrect end behavior. A polynomial has to either go to positive infinity or negative infinity. This one looks like it's going to 0. This one seems to have a horizontal asymptote at y equals 0. So neither of these two can be polynomials. And that seems to be our last example.